It's time for our last application of physics with calculus, and that will be force and pressure. Now, remember from some science class, hopefully somewhere, that pressure is force acting over an area. It's measured in pascals. Pascals are the same as newtons divided by meters squared. This is particularly important when talking about fluids like water or air, since we need to know how much pressure they exert. Now, hydrostatic pressure is the amount of pressure exerted on an object by the stationary fluid that is directly above it due to the fluid's weight. This pressure has the same magnitude in all directions at any particular depth or height. In other words, once you're at a depth, then this hydrostatic pressure is the same everywhere at that depth. Now, hydrostatic pressure is force divided by area. So it's rho G, G being, of course, gravity, times H, where H is your height or depth. So to give you an example of how the units could work here, rho would be your density. And we've already seen density, say, for water. It's, for H2O, it's 1,000 kilograms per meters cubed. Then gravity, which is G, that's the force due to gravity. And that would be 9.8 meters per second squared. We've already seen that before. Those are just the standard issue density and gravity for water on Earth. That's because it's water. That's because it's Earth, right? Okay, so if it's something other than water, then it would have a different density, obviously. And then the height or depth would be measured in meters, right? And so that would get us kilograms divided by meters seconds. So it would end up being pascals, right? So it would be Newton meters squared, or newtons divided by meters squared, I should say. Okay, so let's do a simple example. And this is just going to be really straightforward. There's no calculus to this particular example. If you'll notice, I haven't introduced an integral yet. So there's no calculus yet, just going over the basics here. So free diving is a form of underwater diving that is done by crazy people. Oh no, sorry. So they relies on the diver's ability to hold their breath until resurfacing. So they don't use oxygen tanks. They just dive down with usually a really big fin. You can see right there. So they dive really far down on one breath. They go as far as they can and then they resurface. Hopefully, because if they don't, they have drowned. William Trowbridge holds the world record for free diving. He drove 100 meters, that is the length of a soccer pitch or a football field in other countries, below the surface of the ocean with no oxygen tanks. What was the pressure on his body at his world record-setting depth? Right, result in kilopascals. For comparison, pressure at sea level, just in case you're wondering, is 101.325 kilopascals. So there we go. All right, so again, there's no calculus to this. This is just a straight basic physics problem here. So very basic. So pressure, by definition, is rho, which is the density of water, times gravity times height or depth. Now we already said rho is 1,000. That's just what water is. And again, I'm going to put the units in here so we can see it. So kilograms per meters cubed. So that's rho. Actually, I'm going to color code these. I take it back. So rho times gravity times height. Right, so I'm leaving myself some space in there, but you get it. All right, now gravity, because we live on planet Earth, is meters per second squared, 9.8 meters per second squared. So that's not changing. Now, his depth, aka height, was 100 meters below the water. It's crazy. Okay, so let's see here. I mean, good for him and everything, but I think he's crazy. I don't even need a calculator. This is 980. That's 0. Move that one over 2 spaces. And then this will move it over 3 more. So it's, or did I go too many? Yes, I went too many. There were 5 zeros and it was 9.8. Whoops, my bad. Sorry. There we go. I mean 980,000. There we go. 5 decimal places over for the 9.8. All right. So, and again, check me on Desmos. Now let's look at this. it's kilograms times meters. Actually, I'm going to cancel. Well, kilograms times meters squared over meters cubed seconds squared. Now recall, newtons are kilograms times meters over seconds squared. So if I take a kilogram, let me take it this way. If I take a kilogram of meters and a second squared, if I take these three together, kilograms, meters, seconds squared, that's newtons. And then I can just cancel one of these with one of these and make it meters squared. So it's newtons over meters squared, right? So it'd be newtons over, sorry, I had too many S's in there. Newtons divided by meters squared. But newtons divided by meters squared, that's force divided by area, that's pressure, that's pascals. So it's 980,000 pascals, which I wrote right here. A pascal is a newton divided by a meter squared. So a kilopascal would, of course, kilo means 1,000, right, for our metric prefixes. So that would mean 980 kilopascals. Now think about that. 980 versus 101. He's about, well, he's a little bit over 9 times the amount of pressure as at sea level. That's amazing, right? His lungs were able to take it. I can barely handle diving down the deep part of a pool at like 12 feet. And he is way past that. He's got 9 times the pressure on his body at that depth than he would at sea level. So far, there's no calculus yet. Okay. That was just, kind of a basic, this is how pressure works. Because pressure, we're assuming, is not something you've seen as much of, say, as work in physics. So now, how do we deal with this for a problem that varies? What are we going to vary? And the answer is, well, we're going to let the height vary and we're going to let the pressure vary. So, well, it's not the pressure so much. Well, you'll see. So when we want to find pressure and force on a vertical dam wall, basically, right? So we often take it to be the base of a dam. So you say, hey, I'm going to find out the pressure in the vertical direction on a dam, right? And we choose a convenient origin, usually the base of the dam, but not always. And by dam, I mean a dam, like holding back water. So for example, the Hoover Dam, this is a very famous dam. Obviously real dams have some arch to them. We're going to kind of ignore that at this point. We're going to pretend it's vertical. So it might be better to think of it as the side of a trough, for like a water trough for an animal. Although perhaps a very big water trough. Little image here. Yeah, like one of these. So you can imagine, okay, so if that's my concrete trough, what's the pressure on the side of this trough, right? That's what we're looking at. Or for the particular picture we're looking at on this page, it's more a trapezoid like this. So if you see the side of that trough is a trapezoid, and that very much matches the picture we've got. That's what we're looking at. So what's the pressure on the side there? So the base of the dam, and it can also be a trough, like a water trough. That kind of thing. Oh, I guess I should put it here. That would be a better place to put it. That's the kind of thing you feed animals or water animals from. And you can feed them too, depends on what you're doing. Okay, so we're going to find the width function. We're going to find the depth function. And if the base of the dam is at y equals 0 and the top of the dam is y equals a, right, which is a big assumption, but if we do that, then we would assume that we're going from 0 to a. So they're saying, hey, if you let the bottom of the dam be 0 and the top of the dam be a, which is a very good assumption, then you'll be going 0 to a for your integral to find the force acting on that dam. Okay, so let's look at these force options here. We have rho, which is, yet again, density. Right, one more time. All right. And if it's water, it would be 1,000, but it's in kilograms per meters cubed. Then we have gravity. Gravity is in meters per second squared. Then we have the depth right here. Height or depth, it depends on your point of view. So height / depth. I guess I can put it here. All right, let me show you where that is. So if you take the bottom of the trough or bottom of the dam to be 0, so we say, hey, this is y = 0 down here. Actually, I highlighted it in green, so I'll do it in green. So if I say, hey, this is 0 down here at the bottom of the trough, right there. And then I say that, well, let me put it this way. H of y would be the depth, right? H of y is this distance right here. Right? It's how far down that wedge of water is. And it's measured in meters, right? So that would be in meters. And then, of course, by the way, it's up at a height of y. We can even say that. So I'm just trying to think of a color choice here. So this, they tell us right over there, this is y, right there. So that's y, that's h of y, some function of depth. And then we have w of y. W of y is going to be the hardest part. W of y is the width. It's literally the width of the slice of water that you're looking at, or the slice of dam wall that you're looking at. Okay, so that's going to be the most tricky part because it goes from one end of the trough to the other. So it's from this side to this side. That's W of y. It's also measured in meters because it's a width, right? So for this particular wedge of water, W of y is right here. Right there. Okay. And then, of course, the thickness, dy, right? dy is this right here. Thickness of that little wedge that you're looking at on that plate, on that edge of that trough. And it would be measured in meters, of course, because it's a thickness, it's a vertical distance. All right, so figuring out all the units really quickly, if this is going to work. We have meters cubed down here, and then meters, meters, meters. So if you cancel, meters cubed cancels with this meters, and this meters. Leaves you kilograms, meters, and seconds squared. And kilograms times meters divided by seconds squared is newtons, right? So it is going to work. This is going to get us pressure, right? The force acting on the side of the dam or the side of the trough. Again, you imagine a little strip. It's sort of like the wedge of water when you were doing volume for the pool, right? And then imagining lifting that water out of the pool for the lifting problems. It's sort of like that, but you're only looking at a strip along that side of that dam or that trough. So you look at that strip, it's at a height of y, it's at a depth of h of y. It has a width, which is w of y. It has a thickness, which is dy. And then water is usually what we're holding back, but you know, water and earth, or I guess I should say fluid and earth. Whatever fluid you're holding back will have a density, and then you live on Earth, so it'll be gravity. Unless we're doing Mars, which will be simply a different one. Okay? And then the pressure, if the water is all the way to the top, the pressure is from 0 to A, and that's why you're adding for your integral from 0 to A. Of these things, by the way, the hardest one to find by far is going to be the width. The width is going to be the most difficult part to figure out.